Good morning, everybody. Welcome back to Math 105. Plan for today is we are going to finish our discussion of truth tables. Or, at the very least, we're going to finish our discussion of Standard 5, which is about these truth tables. After today, on Friday, we're going to start Standard 6, in which we'll be using truth tables to sort of look at some classical laws of logic dating back hundreds and hundreds of years. As far as office hours go, I've got my usual office hours today and tomorrow. Today at 10, from 10 to 10:50, and from 2 to 3. Tomorrow morning from 10 to 11, and tomorrow afternoon from 1:30 to 2:30. As far as homework goes, Standard 5 quiz is going to go up sometime later today or tomorrow. It will be due, when I say it's due, probably I'll make it due over the weekend or on Monday. But I'll send an email out with that information. Also, we're a week out from our first exam. So, first exam is going to be next Wednesday. It will be over Standards 1 through 5. Format of the exam. I was hoping to tell you exactly what the format of the exam is going to be today. But I'm still struggling to figure out if I can do what I want to do with the exam on Blackboard. Because Blackboard, as you know, does not really like cooperating with me for this mastery-based stuff. So, I'm going to talk a little bit generally about about kind of my expectations for the exam today, and then on Friday, I'll talk more about the specific format of the exam. So specifically, I'm not sure if I'm going to be able to do what I want through Blackboard, or we might end up having the exam just in class next Wednesday. But I'm going to figure that out in the next day or two. And then on Friday, we'll have a discussion where I'll tell you exactly how it's going to go. But a few comments about the general format of the exam, though. It's basically going to be like 5 quizzes. You'll have 50 minutes to work on it, so I plan on giving you 10 minutes basically per standard. No matter what the format is, it will be open notes. So you'll be able to kind of use your notes, go back to your packets to help you out. And just like with the quizzes, if you fail to get a mastery on every single exam question, it doesn't affect your grade at all. This is just kind of this first exam is just going to be an opportunity for you all to kind of earn up to 5 masteries in a single go. But you will have more opportunities to earn lots of masteries in a single go. This is only the first of 4 midterms plus a final, all of which are going to have Standard 1 through Standard 5 questions. And so this exam, I hope for you, is not something that you stress out about. It's not like your typical math exam where you need to get a certain percentage or however many points on it. If it goes poorly for you, you still got a lot of semester left to kind of take retests and do well on those standards.
If we, let's say, have already 2 masteries on Standard 1, are we allowed, I don't remember when we reviewed this in the first class, but could we skip Standard 1 if you already have the 2 masteries for Standard 1 on the exam? Or do we take all of them?
So the question is, if you already have 2 masteries on a standard, do we still have to do the exam question? And my answer is no. If there are any standards that you already have 2 masteries on, from say, maybe from doing the quiz A and the retest, you then get to skip those questions on the exam. So depending on how you've been doing, maybe you only need to come into the exam and do 2 or 3 questions, and you get to leave, and you get to quit the exam really early. If that is you, then more power to you. If you need masteries in everything, though, and you want to take the full 50 minutes, then that's also perfectly fine. It's basically going to just be time for you to plow through as many as you can. And the format, I'll write each individual standard problem to be about the same difficulty as, I'll try and make it similar to what you would see, what you've been seeing on these Blackboard quizzes so far. But yes, it will be open. Yes, it will be open notes. You have full 50 minutes to work on it. It will have 1 question from each standard. And just like the Blackboard quizzes, when I say 1 question from each standard, I might say Standard 1 might be like a part A, B, and C or something. as you've seen for some of these, like a single question is not just going to be negate this statement, but it might be negate this statement, or and explain why these two things are logically equivalent, something like that. Yeah, so that's all my comments for now. I'll give detailed instructions on how the exam is going to be formatted on Friday. Any other questions or comments before we get started for today? How are mathematicians like the Air Force? Mathematicians are like the Air Force in that they both use pilots. Pilots. Okay, so last time we had started our discussion of truth tables. We kind of got about halfway through Standard 5. We talked about truth tables as sort of being a way of seeing if two statements mathematically are logically equivalent. And the idea was in drawing a truth table, you don't have to write this one down. This one we talked about on Monday should be on like the front page of your packet if you've been taking notes. The idea is that we have these pre-filled columns that correspond to sort of the individual statements that are going to be part of your truth table. So in this case, P and Q. And the idea was we started by filling in basically all the possibilities for P and Q being true and or false. So in this case, we had the possibility where P and Q are both true, where one is true and the other is false, and the possibility where P and Q are both false. That kind of covers all our bases, all four possibilities for P and Q. And then once you kind of fill in these pre-filled columns corresponding to the individual statements, in this case P and Q, we had these other columns that you could fill in based on when are these kind of compound statements true. For instance, P and Q is only true when both P and Q are true, whereas P or Q is true if both P and Q are true, or if exactly one of the two is true. If P then Q is true except in the situation where P is true, Q is false. And finally, P being logically equivalent to Q, we said is true in the situation where P and Q are both true or both false. And truth tables were helpful for us in that if we drew a truth table and we found two columns that appeared exactly the same, like two columns, like let's say we had some other statement X that had true, false, false, true. If we have two columns like this, where they're the exact same, the same sequence of truths and falses, that told us these two mathematical statements have to be logically equivalent. So whatever statement X is, for instance, would have to be logically equivalent to saying P and Q are logically equivalent. And last time we looked at examples kind of in class in which we kind of looked at negation and connectives, and where we actually proved De Morgan's laws, proving the negation of an and statement is an or statement, and the negation of an or statement is an and statement. So what I wanted to start with today is looking at a few different, seeing if we could prove a few different mathematical equivalences using truth tables that involve implications somehow. Because we didn't really do any examples with this column, the if P then Q column, on Monday. So in particular, I would like to show that the negation of if P then Q is logically equivalent to saying P and not Q. I.e., we can say that P implies Q is only false when P and not Q is true, and vice versa. This is something we talked about back in Standard 4, that the negation of an implication, the negation of if P then Q, we said was logically equivalent to the and statement P and not Q. And it's a little bit, I know this one is one that a lot of you have struggled with in looking at the quiz 4s. And so thought we'd kind of go through this one as an example way of sort of getting a better sense of why is it the case that the negation of an implication actually turns into an and statement rather than just another implication. So let's see if we can do this with a truth table. So to start, we're going to need our columns for P and Q. We ultimately like to be able to get columns for negation of if P then Q, and a column for P and not Q. And we'd like to be able to show that the columns for these two mathematical statements appear the same in our truth table. So what would be some useful columns to start off with? We already have columns for P and Q individually. I don't want to go right into making columns for either one of these statements, since both of these statements are a little bit complicated. What would be some useful kind of starting columns to help us start out?
If P then Q.
Just P, if P then Q without the negation?
Yes.
I think that would be good, because if we have a column for if P then Q, we can then use that to get to a column for the negation of if P then Q. If P then Q just by itself is a good stepping stone for getting from columns P and Q individually to the column negation of if P then Q. So if P then Q, as we've seen, is going to be true in every scenario except the second one, where P is true and Q is false. So what would the negation of if P then Q look like in this case? If P then Q has true, false, true, true, if we're negating that, meaning we need to swap all our trues with falses and vice versa, what would the negation column look like?
It would be false, true, false, false.
False, true, false, false. Our three trues become falses, and our one false becomes a true. So the negation of if P then Q, in other words, is only going to be true in the case where P is true and Q is false. So I'd also like to be able to get to a column for P and negation of Q. We have columns for P and Q individually. What would be a useful column to add in that would allow us to kind of get from our first two columns to P and not Q as a stepping stone?
Negation of Q.
Yeah, just a not Q column. Because if we have a P column and a not Q column, that's going to allow us to get to P and not Q fairly quickly. So if Q is true, false, what would the negation of Q look like? In other words, if we swapped our trues and falses, what would we get?
False, true, false, true.
False, true, false, true. Trues, or two trues become two falses, our two falses become two truths. And so now that we have a column for P, and we have a column for not Q, we can use that to find a column for P and not Q. For this time, it's a little bit tricky because our P column and our not Q column are really far away from each other in the truth table. One's kind of here, and one's all the way over here. So, in the case where P is true and not Q is false, what would be the truth value of P and not Q if the first is true and the second is false?
False.
It's going to be false. How about the case where P is true and not Q is also true? What would our and statement be?
True.
It's going to be true. If P is false and not Q is false?
False.
And the last case where P is false and not Q is true?
False.
Also going to be false. Yeah, exactly. Here, if you're trying to do something like make an and statement column for two other columns that are really far apart like this, P's all the way over on our left side of the table, not Q is way over here. It helps me to sometimes maybe draw a little kind of line like this to connect. All right, these are the two columns where we're joining with an and statement. It's not something that's strictly necessary, but it's something that I find helpful to help me keep track of. All right, what were the two columns we needed to take an and for? This one and that one. So what do we notice looking at this truth table?
The negation of if P then Q, the truth table is the same for P and not Q.
Yeah, if we look at the not P, if we look at the negation of the implication column, we get false, true, false, false. If we look at the P and not Q column, we also get false, true, false, false. So in other words, the fact that this column comes up the same as the last column tells us that the statements for these two columns have to be logically equivalent statements. Since their columns are the same, negation of if P then Q and P and not Q are logically equivalent. So one way that you can describe why the negation of an implication is this and statement, it comes down to the fact that in 3 out of 4 scenarios, both are going to be false. And there's only a single scenario where both the negation of the implication and this and statement, P and not Q, are both true. The only scenario where they're both true is this one, where P is true and Q is false. That's the only way to make the implication false, and hence its negation true. And true false is also the only way to make P and not Q true. Meaning that since the negation of the implication and this and statement, since they're always true at the same time as well as false at the same time, they have to be logically equivalent statements. Any questions or comments about what we did here? Okay, let's go on to the next page. Another statement that we made back in Standard 4 about implications is that if we were to take the contrapositive of a mathematical statement, meaning if we were to take if P then Q and swap it out with if not Q then not P, that both of those statements, we said, have to be logically equivalent. In other words, we said that P implies Q is logically equivalent to saying not Q implies not P. Where this one was our original implication, and this one was our contrapositive. So in other words, we could say the statement, if Tom is a cat, then Tom chases mice. Shout out to Tom and Jerry. Cartoon about cat chasing mouse. If this was our original implication, what would the contrapositive of this statement be? The statement that we could say has to be logically equivalent to this.
If Tom is not a cat, then Tom is not chasing me.
So this one is our P implies Q, and you claim that our not Q implies not P is that if Tom is not a cat?
Isn't it if Tom is a cat, or sorry, Tom is not a cat and Tom does not chase mice.
You're close. We definitely need to negate both those statements somehow. I guess.
It'll be able to flip the community around, so if Tom does not chase mice, then Tom is not a cat.
I think so. If Tom does not chase mice, then Tom is not a cat. So if this one is our P, Tom is a cat, and this one is our Q, Tom chases mice, if we're going to take our contrapositive and get our not, if not Q, then not P, we first need to write down the negation of the Q, if Tom does not chase mice, and then we can write down the negation of our P, Tom is not a cat. I think the first one you said was the inverse, if not P, then not Q, which is not logically equivalent, but is closely related, I will say. So according to this kind of rule of mathematics, these are the sorts of statements we're saying have to be logically equivalent. If Tom is a cat, then Tom chases mice. And if Tom does not chase mice, then Tom is not a cat. Because according to this, all cats have to be mice chasers. Meaning if we're outside the circle of mice chasers, we certainly have to be outside the circle of cats as well. Both are making this sort of claim. If we're in the cat circle, then we're in the mice chaser circle of the Venn diagram. Or equivalently, if we're outside the mice chaser circle, if we're outside this big circle, we also have to be outside the inner circle.
That's why my original one couldn't work, because you can't be outside of the cat circle but still be in the mice chaser circle.
Sure. If, I don't know, what else chases mice besides cats?
Foxes.
Foxes? I heard oxes at first, now I like that better. That's what I'm going to go with. Let's say it's possible to be, say, like an ox that chases mice, but not a cat that chases mice. And so it's possible to be in the mice chasers circle outside the cat. So if not P, then not Q doesn't quite work in this scenario. But if we're outside the mice chaser circle, we certainly also have to be outside the cat circle. There's no way to be outside the big circle and inside the small one. Good question, I'm glad you asked. All right, truth table. I'm going to fill in my P column as true, true, false, false. I'm going to fill in my Q column as true, false, true, false. And the rest of this table, I want you all to take a few minutes and think about. So go ahead and take a couple minutes and see if you can construct the rest of the truth table in a way that'll let you show if P then Q has to logically be equivalent to if not Q then not P. Go ahead and take a couple minutes. As always, if you feel comfortable doing so, you can talk to your neighbors and we'll reconvene as a class once you've had a chance to think. If you finish your table, and if you feel comfortable doing so, I encourage you to check with your neighbors, see if they got the same sort of final columns as you did. You seem to hear your neighbors. I will say I got the same thought. I can do. Things be tricky. Okay, so walking around the room a little bit, I can see some sort of similar ideas that you all have been having. What was the first? Anyone like to give us a candidate for the first kind of a new column that they made that they found helpful? Just an if P then Q column? Yeah, so that's something we can get to just from the P and Q columns. We don't need any extra stepping stones to get to that one, I don't think. Okay, what did you find in your if P then Q column?
True, false, true, true. False, who's true, who's false.
Bingo. Yeah, so the if P then Q column is going to give us a true, false, true, true, as we've seen before. I think we might want to have a couple stepping stones to help us get to a column for the contrapositive, the if not Q, then not P. So did anyone have a stepping stone column or two that they found to be particularly helpful here?
Negation of Q and negation of P.
Just individual columns for the negations of the individual statements?
Yeah.
I like it. I found that helpful myself. Okay, let's make columns for us. What did your negation of Q column look like?
False, true, false, true.
False, true, false, true. Since the Q column is true, false, doing the switcheroo on all those would give us a false, true, false, true. Someone like to share what their negation of P column looked like?
False, false, true, true.
False, false, true, true. Switcheroo of true, true, false, false. And then I think from here, we're ready to make a column for if not Q, then not P. And to me, this one was the trickiest one.
I got true, false, true, true.
True, false, true, true. Let's see. If the two individual statements, not Q and not P, are both false, the implication has to be true. If the first one's true and the second one's false, then that was our only time when the implication is said to be false. If first statement's false, second statement doesn't matter. Implication has to be true. And finally, if both not Q and not P are true, then the implication, if not Q, then not P, is also going to be true. What do we notice?
The if P then Q column and the not Q then not P column have the same true values on them.
Gadzooks. Yep, we have two columns that come out to true, false, true, true. And so I think using that, we can actually say our result. We're going to say, since they have the same columns, if P, then Q, and if not Q, then not P, must be logically equivalent. Why do I keep writing this sentence down every time after we do our truth tables? You notice that I've been making a pattern of this. Every time we make a truth table, find that two columns are the same, I write down this extra sentence about, since they have the same columns in the truth table, blah, 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 these two statements are logically equivalent. Why do I keep doing that?
So that we can practice writing out proof for what we just found.
Ooh, so we can practice writing out proofs. Yeah, I would agree. We haven't really talked too much about proof writing quite yet. That's going to be coming in future standards. But one kind of aspect of proof writing that we're going to be doing is, I like to think every proof is sort of like your English papers, has to have an introduction, it has to have a conclusion. And I think writing a sentence like this that basically just says, hey, here's what we've shown. The thing we wanted to show is going to be our conclusion for all of our proofs later on. Just to make it absolutely clear, this is the thing that we've shown, that these two statements are equivalent, coming from the observation that this column and this column come out to the same thing. It's good practice to kind of always have a sentence at the end of your proofs like this, I think, just to make it clear, this is what we've shown, and this is why it had to be true based on our previous work.
So for the quiz, for the standard, would we have to put a truth table on how we would do that? We would just put the last sentence?
How would you write a truth table for a quiz?
Yeah.
Oh, gadzooks, how our truth table is going to work through Blackboard. Don't worry. What I'll do on Blackboard is I'll have a truth table with blanks in it that you'll be able to fill in. Should be able to. There's a reason why the standard 5 quiz hasn't come out yet, because I need to play around with actually doing that. But that's going to be the plan. Any other questions or comments? Okay, so next up is going to be the last kind of big thing we talked about at the very end of Standard 4. I kind of mentioned this as a passing thought, but this time we're actually going to go through and look at this claim carefully. I claim this. How's that for a lovely compound statement right there? How can we put this statement in words? If we were to try and kind of sum up what this symbolic statement is saying using kind of a sentence in English, how could we do that? This one's a bit tricky since it has so many different pieces. I count 2 double arrows, 2 single arrows, as well as an and popping up.
If P, then Q, and if Q, then P is logically equivalent to P, logically equivalent to Q.
Yeah, so we can say this. I'm going to say if P implies Q, and Q implies P, let's get drop the P implies Q and Q implies P is logically equivalent to saying P and Q are logically equivalent. Which is a mouthful of a sentence. So to put it in maybe try to make this a little bit easier to read, we could say kind of more simply, to show P and Q are mathematically the same, meaning to show P and Q are logically equivalent, what we can do is we can just show that each statement implies the other. So in other words, P and Q can be said to be mathematically the same statement if P always implies Q and if Q always implies P. That's one way of kind of showing formally that P and Q are mathematically the same statement. Is each statement implies the other. So before we go on to drawing a truth table, since that's a bit of a complicated statement, I thought we could do an example and maybe look at a Venn diagram to sort of see what's going on here. So here's the example I have. If it is a water demon, then it is a mermaid. And if it is a mermaid, then it is a water demon. Suppose we have a lovely compound statement like this, and let's say we're assuming that this statement is true. If it is a water demon, then it has to be a mermaid. Let's say we're assuming we've seen some sort of creature in the water. If it is a water demon, then it is a mermaid. And also, if it is a mermaid, then it is a water demon. Sorry if Anne's a little mermaid on this example. What are we saying is the relationship between water demons and mermaids?
They're the same thing.
They're exactly the same thing. Because this statement, this first piece, is really logically equivalent to saying all water demons are mermaids. The second statement is logically equivalent to saying all mermaids are water demons. If all water demons are mermaids, and if all water demons are mermaids, well, that tells us being a water demon and being a mermaid are logically equivalent things, since being either one automatically implies that you have to be the other. So it is a water demon is logically equivalent to saying it is a mermaid, which in IE, by the way, standing for it-est, in other words. Water demons and mermaids are the same creatures. Your definition of water demon may not agree with this. So, those of you who've seen Harry Potter, for instance, there's lots of water demons in that. But let's see how this works with a Venn diagram. Like if you flip the page, I give you space for this. What would the Venn diagram look like for if it is a water demon, then it is a mermaid? How could we sort of draw a Venn diagram that would represent this thing visually.
Wouldn't it just be a single circle? Two circles that completely covering each other?
The compound would be. How about just the first part for now? Just the if it is a water demon, then it is a mermaid part.
Water demon circle with smaller circle inside as a mermaid.
I think that would actually be the case for.
Would be a water demon circle with a mermaid circle around the water demon circle.
Yeah, I think the water demon circle for this first part is actually going to be the smaller one. Let's just say WD. Because if we're saying all water demons are mermaids, if it is a water demon, then it is a mermaid. What we're really saying is that the circle of water demons has to lie entirely inside the mermaid circle. So if this is our P and this is our Q, we would be saying something along the lines of the P circle lies entirely inside of the Q circle. And then the second half, if it is a mermaid, then it is a water demon. How would that visually look different?
It would be the inverse of the Venn diagram, like Anna was saying. So it would be the mermaid now in the smaller circle, and then the water demon would be the bigger circle.
Exactly. Here now we're saying the mermaid circle lies inside of the water demon circle, or equivalently that the Q circle lies inside the P circle. And here we can say if each circle has to lie inside the other one, then I think we go here describing Anna that they have to be the exact same circle. The only way for one to be inside the other and the other to be inside the first was if they were the exact same circle to begin with. So, in other words, our P circle and our Q circle have to match up exactly. Or our water demon and mermaid circles have to completely overlap. It's the only way for both circles to be inside the other circle. If P is inside of Q and Q is inside of P, have to be the same circle. Otherwise, we get some sort of logical paradox where you have a P inside of a bigger Q, inside of a larger P. But they're the same P. Kind of mind-blowing. Any questions or comments before we go on to drawing our truth table? Okay, go ahead and take a couple minutes. See if you can draw a truth table now that actually will show if P then Q and if Q then P is logically equivalent to saying P and Q are logically equivalent. Sorry to have to kind of cut you off here, just a few minutes early, but just want to make sure we have enough time to finish talking through this example as a class. So we have a P and Q column. My if P then Q column looks like true, false, true, true. Same as we've seen in kind of all of our other examples so far. I found it helpful to have an if Q then P column. Anybody like to share what their if Q then P column ended up looking like?
I put true, true, false, true.
True, true, false, true? I like it. Nice column. So I think our if Q then P column has to be true, true, false, true, because the only way for if Q then P to be false was if our first statement Q is true and if our second statement P is false. So if we have if these two columns for if P then Q and if Q then P, what would it look like if we drew a column for if P then Q and if Q then P?
True, false, false, true.
True, false, false, true. Let's see. If they're both true, this is true. If one is false, then the and statement's false. If one is false, the and statement's false. If both are true, then our and statement has to be true. Which, as we've seen before, should be matching up with our P and Q being logically equivalent column. Because we said that was true, false, false, true, because this column is only going to be true if P and Q are the same thing. P and Q are both true, or if they're both false. Anybody sum up in a kind of our sentence that kind of goes after the end of our drawing our truth tables?
Since they have the same columns, if P then Q and if Q then P, and P is logically equivalent to Q, must be logically equivalent.
That's a mouthful, but I agree. Absolutely. Since they have the same columns, P implies Q and Q implies P must be logically equivalent to saying P and Q themselves are logically equivalent. Just so you know, on the quiz, what I'm probably going to do is I'm probably going to give you like a partial truth table and then ask you to fill the rest in and then write a sentence to explain what you found. If I ask you to write a sentence explaining what you found, it's going to be something like this. Just notice they have the same columns, therefore logically equivalent. Okay, it's going to do it for Standard 5. I lied to you in the syllabus. Standard 6 is not what the syllabus says it is, because we already talked about what the syllabus says in Standard 6. So we're going to be talking about classical laws of logic on Friday, get into a little bit of history. Have a good one.
Thank you.
Nice job today.